In this video, we're gonna take a little digression and talk a little bit about the X functor. Recall that previously we have given two ways of defining the cohomology groups of a given group G with coefficient in A. One way is via the right-derived functor of this G-invariant functor, which could be viewed as the covariant home functor represented by Z. Another way of defining these cohomology groups with coefficient in A is via the right-derived functor of the contravariant home functor represented by these coefficient A. The fact that these two definitions are equivalent is an instance of a more general phenomenon. In the category of modules over a fixed ring R, we have two types of home functor, two types of representable functors. One is covariant and one is contravariant. Both types of home functors are left exact, and since the category of R module has enough injectives as well as projectives, we can talk about the right-derived functors of these left exact functor. It turns out that if we evaluate this right-derived functor at A, we get the same abelian group that we would get if we evaluate this right-derived functor at M. This common abelian group is denoted by X. The notation X is short for extension, and that comes from the fact that X1 of any two R modules M and L classifies equivalence classes of extensions of M by L. In this video, we want to look at a few examples to get a feel for this X functor. First, observe that if P is a projective R module, then XP is always going to be 0. Dually, if I is an injective R module, then X of blank comma I is always going to be 0. So why is that? This is simply due to the fact that a left exact functor f is exact if and only if the right-derived functors of f all vanishes in degree greater than or equal to 1. Indeed, if f is exact, then applying f to this short exact sequence should result in another short exact sequence. In particular, all of these must be 0. Conversely, if all of these are 0, then that means that the result of applying f to this short exact sequence is a short exact sequence. This is, of course, no surprise because the right-derived functors are meant to measure the extent to which f fails to be exact. Now coming back, recall that by definition, P is projective if we can always lift morphism from P. In other words, if and only if this functor preserves surjectivity, i.e. if and only if it's right exact, and thus exact because it's already left exact. By the previous discussion, we see that this means that its right-derived functor must be trivial in all positive degree. Similarly, by definition, I is an injective R module if and only if we can always extend morphisms to I. In other words, this contravariant functor sends monomorphism to epimorphism, i.e. it's right exact and thus exact because it's already left exact. So that again is equivalent to saying that its right-derived functor must be trivial in positive degree. Alright, so that's the value of the X functors on projective and injective modules. Next up, let us compute some examples of X group. Let us compute the X groups of Z mod MZ and A viewed as Z modules, i.e. abelian groups. In degree 0, this is just a group of group homomorphism from Z mod MZ to A, which is isomorphic to the group of M torsions inside A. Why is that? Well, that's just because the zeroth right-derived functor of any left exact functor f must be equal to f. Now here we could view this as the zeroth right-derived functor of this left exact functor evaluated at A. And as we said, that's just going to be equal to this functor here evaluated at A, which gives us this home group. Of course, we could also have viewed this as the value of the zeroth right-derived functor of the contravariant home functor, and then evaluate it at Z mod MZ. The answer will be the same. Since these could be viewed as right-derived functors of two different functors, we could compute these X groups using either an injective resolution for A or a projective resolution for Z mod MZ. We'll choose the latter because it's very easy to find a projective resolution in this case. The key idea here is that free modules are always projective. For example, R is projective as an R module. This is because R is generated as an R module by a single element, and thus every map from R is uniquely determined by the image of 1. In particular, if we have a surjection of R modules M and N, then we can always lift phi to M by sending 1 to any elements in the fiber here above phi of 1. Thus, R is projective, and the same argument shows that any free R modules are projective. Thus, to find a projective resolution for any given module, we just need to find a free resolution. For example, we have the following free resolution for the Z module Z mod MZ. We get this map here by observing that Z mod MZ is generated as a Z module by a single element 1. So we have a surjection from the free module on 1 generator to Z mod MZ, sending 1 to the generator of Z mod MZ. The kernel of this map is a free Z module of rank 1 generated by the single relation that this generator 1 has with itself, namely M times 1 is equal to 0. If we identify this module with Z by sending the generator M to 1, then this map becomes multiplication by M, because the image of the generator must be M. So both of these short exact sequences correspond to the same presentation of Z mod MZ as a Z module, and we can use either of them to compute these X groups. Let us just use this second one. Recall that we are viewing these X functors as right-direct functors of the home blank A functor. So to compute these X groups, we need to apply these home blank A functor onto this projective resolution. This gives us a cochain complex, and recall that these X groups were defined to be the cohomology groups of this cochain complex. Since this cochain complex has only 2 non-trivial terms, we know that these higher degree X group are gonna vanish. Thus, it suffices to find the cohomology group in degree 1. To do so, observe that any homomorphism F from Z to A is uniquely determined by where it sends 1. So by sending F to F of 1, we get an isomorphism between this group and A. Now, what is this coboundary map under this identification? Recall that the coboundary of F was just defined to be the lift or the pullback of F under this map. In particular, the coboundary map of F sends 1 to F of M, which is just M times F of 1. Thus we see that this map is just multiplication by M. Thus, the first cohomology group of this cochain complex is just the kernel of this first coboundary map, which is A, quotient now by the image of this coboundary map, which is just MA. Thus, we have found all of the cohomology groups of this cochain complex, and hence all of these X groups. Note that the fact that these X groups vanish in degree greater than or equal to 2, it's actually true for any 2 general Z modules. This is because every Z module, and more generally every module over PID, can be injected into some injective module, but quotient of injective modules over PID are also injective. Thus, every module over PID has a 2-term injective resolution. Thus, if we compute this X group using the injective resolution of A, we see that all X group in degree greater than or equal to 2 must vanish. Now, before we end, let us just quickly remark that the same abelian groups, when viewed as modules over different rings, will result in different X groups. For example, had we viewed these groups as Z modules, then this X group would have been trivial. But if we view them as Z mod MZ module, where D divides M, then we'll see that none of these X groups are gonna be trivial. Alright, so that's the end of our digression. Up next, we are gonna come back to computing group cohomology by looking at some specific projective resolutions of Z.